Nuclear physics at Notre Dame has a long history from very beginning of the field. Actually, from the mid-30s, there was an accelerator here. We decided together to form a bigger vision of where we were going and concentrate on both hiring people and also running experiments in our facilities. Nuclear physics at Notre Dame has many aspects. We look at the entire sort of birth of stars, the evolution, how stars live and die, to how they contribute to the evolution of the cosmos itself. Our process has become a really central focus for nuclear physics all over the world. It's not just us at Notre Dame that are interested in it. The facility that's being built at Michigan State, the FRIB, had a major motivation of it was to try and study very neutron-rich nuclei that are potentially produced in the R process. It's no longer that an individual area of study is just making contributions and advances on its own. We are at a point in knowledge that we need all of the other aspects of science to play. So we understand how nuclear reactions take place, what the nuclear physics influence is, but we need to know in what kind of environment nuclear physics is operating in. And that's the major focus of my research here in collaboration with Rebecca Sermon on the theory side and with the group at Argonne on the experimental side. But also MSU and Uvascular. So Rebecca's a nuclear theorist with special interest in the nuclear astrophysics side.
One of the major open problems that I'm working on these days is the origin of the heaviest elements in a process called rapid neutron capture, or our process nucleosynthesis. The question is, where did the neutrons come from for this rapid neutron capture process? Basically, my research is to look at this problem in a different angle. I'm trying to say, can we use the ratios of the abundances of heavy elements that we see in the galaxy to tell us where the astrophysical site is? Why haven't people done this in the past? Well, the problem is that all of the nuclei created in this event are very far from stability and most of which have never been seen in the laboratory. Therefore, we don't understand their nuclear properties. We have to model them. And those models have large uncertainties. One of the things we've been working on recently is to see what effect do those nuclear uncertainties have on our predictions for these astrophysical environments. We're heading off into two different directions. We want to look at, number one, what pieces of nuclear data do we need to know better in order to make these precision predictions that we need? Assume that we can know the nuclear data better, then how can we use abundance patterns to get at the details of the astrophysical site?
No scientific effort today is possible without collaborations, both nationally and internationally. And in fact, our faculty at Notre Dame have collaborated with Michigan State in designing a recoil mass separator, SACAR, which is now funded by the DOE. We collaborate in contributing both design, equipment, and so on, as well as collaborating with using other people's equipment and instrumentation. Manuel Couder, he is very key part of installing and implementing the CASPAR project.
Right now at Notre Dame I'm working into two separate projects that are both related to studying nuclear reaction of astrophysical interest in the context of question burning in stars. And so the big questions there are what are the nuclear reactions that fuels the stars, like our sun and bigger than our sun, and what can we learn about the evolution of those stars and how can we link the observation that our astronomer colleagues make with nuclear reaction that we believe take place in those stars. And one way to do that is to continue what our colleague in Italy, for example, did by putting an accelerator underground. This is the Casper project that we hope will open the door to the Diana project one day. And then here at Notre Dame is the usage of a recoil separator called St. George. There we return the standard way of studying nuclear reaction. We use a heavy beam on a light target. This allows us to study the production of the charged particle, increasing efficiency, decreasing the background in the gamma spectra. So in low mass stars, it is believed that a sequence of reaction coming from carbon leads to the production of the neutrons that are then used to produce up to 50% of the element heavier than iron. What St. George will do is to study a competing reaction, which is a neon-22 alpha gamma, and specifically for neon-22 alpha. The combination of the high-intensity beam coming from the new accelerator, the separation properties of St. George should provide us a direct measurement for those critical reactions.
Some unique capabilities we have is the radioactive ion beam facility, the twin-soul dual spectrometer. It was the first radioactive ion beam facility in the US. It's a dual superconducting magnet system that we can use to do reactions. Dan Bardian is particularly interested in nuclear reactions that involve fluorine-18 and neon-22.
This big question I'm trying to answer is, why do some stars live seemingly forever, but other stars explode and die catastrophically? What we study at the Nuclear Science Laboratory here at Notre Dame is the extreme nuclear physics. We produce these exotic nuclei and transport them, separate them with something we call the twin-sol separator. After separating the radioactive nuclei, the exotic ones, we can then measure their reactions. The techniques that we're developing with the twin-sol separator to calibrate proton capture reactions. One of the big questions is, what is the rate of these nuclear reactions? By measuring their properties or by measuring the rates directly using the twin-sol separator, we can then calibrate and determine the astrophysical rates of the very same nuclear reactions occurring in stellar explosions.
Notre Dame's support of nuclear physics has been just wonderful. Since 2012, we have doubled the nuclear faculty, experimentalists. We've hired a nuclear theorist, and in supporting areas, grown in astronomy, so observational area of physics. At the moment, we have 35 PhD students in the nuclear physics program, which is a third of the departments and one of the largest nuclear physics programs in the country.
We have all of the resources of a major research institution, but at the same time, it's small enough to engender collaborations between theorists and experimentalists, between theorists and astronomers.
It allows us to quickly try new experiments. I'm guaranteed the ability to try something within 2 months, sometimes faster, and a lot of times I can produce the exotic nuclei that are so important for my research within just a matter of hours. Being at Notre Dame has allowed me personally to grow my research, to grow in the direction that I want to grow, and a speed that's only determined by how quickly I can think of new ideas.
The commitment of Notre Dame and other universities in nuclear physics is actually critical to keep the field going and to produce new science, critical science in terms of nuclear astrophysics, like we do here at Notre Dame.